Stop, the universe is thinking, and you're part of the thought. The detectors shouldn't care, but they do. We flip a switch after the photon's already flown, and the pattern on the screen changes like it heard us. Out in space, light that left a quasar billions of years ago still answers a choice we make tonight. If that sounds like magic, hold on, it's worse. Your late choice can be space-like separated and the counts still bend. Ancient starlight can set the dials and the pattern still follows. If matter feels even a whisper, we've been asking the wrong question. Is the universe a mind, and are we a thought inside it? 5 anomalies, 1 loophole, 40 seconds from now, the first glitch that refuses to die. The question we've been dodging. Here's the thing, panpsychism isn't a vibe. It's a bet about how matter works. Not that rocks have opinions, you know what, but that every physical thing carries a tiny interior, proto-experience, a minimal what it's like that isn't rich, isn't mindful, just a sliver of feel that comes with having cause-and-effect structure. That's the claim. Tiny, humble, testable, or it's worthless. So what would count as signal? Predictive leverage. Not poetry, not metaphors about the cosmos meditating. We need places where changing information conditions. What's knowable about a system, how it's embedded, nudges outcomes in ways energy alone can't explain. If a theory about feel can forecast non-random deviations when context flips, and those deviations replicate across labs and scales, then we're not in woo, we're in physics with new terms. Zero drop-off rule. Every 30 seconds we raise the stakes and bank a test. Before you flinch, remember the bruise that never heals in quantum theory. The measurement problem. Set up a particle to interfere with itself and you get waves on the screen. Add witch path information and the waves collapse to dots. That's old news, but the trouble keeps leaking out of the lab. We can delay the choice to gather path information until after the particle would have decided, and the statistics still shift. In cosmic versions, starlight born before Earth existed seeds the randomness for our settings, and entangled pairs still violate classical bounds. Whatever's going on isn't waiting for a human to look. It's about relations. What's recorded? What can be recorded? What's redundant in the environment? So the central question, said cleanly, do particles carry internal states that matter for how they relate, not just in position and momentum, but in informational terms? Do systems have an intrinsic side, a minimal integrated cause affect power that behaves like a protofield? If yes, you get a universe where objectivity doesn't float free. It's built as information is copied and stabilized. You also get a path to tests. Change the copying conditions. Watch reality choose differently. The stakes are real. Ethics shifts if harm can ride on substrates beyond brains. AI alignment looks less like stuffing goals into black boxes and more like building systems that write transparent ledgers of their own world models, minimizing surprise without collapsing diversity. Free will gets reframed as constraint writing, our choices as local edits to the universe's ongoing computation. Cosmology, too. If the cosmic web carries not just mass and fields, but network-level memory, forecasts of star formation and lensing noise might need an extra term for information flow. Now guardrails. We're not saying electrons have rich minds. We're saying the minimal claim. If integrated information, call it 5, exists at any scale, even vanishingly small, then protofield tags along with causal structure. Tononi's integrated information theory in its 4th formulation lays out the axioms: intrinsicality, composition, information, integration, exclusion. A system feels to the extent it has irreducible cause, effect power over its own past and future states. That gives you a threshold to estimate, not a license to anthropomorphize. You might ask, so what about brain stuff leaking into physics? Stuart Hameroff and Roger-Penrose updated Orch OR in 2014, arguing warm quantum vibrations in microtubules could sustain coherence long enough to matter for consciousness, with anesthetics disrupting tubulin resonance as a test. It's controversial, and evidence is mixed, but here's the useful piece. Tie conscious level changes to concrete, falsifiable physical signatures. That's the spirit we want. even if the microtubule story ends up wrong. Meanwhile, Vazza-Felletti's quantum Darwinism comes in from a different angle and quietly hands us a tool. Decoherence doesn't just kill superpositions. The environment writes many copies of certain stable, pointer states. Redundancy explodes. Photons, phonons, dust, each carries offspring of the same fact. That's why many observers can agree without touching the system or each other. If the world keeps a ledger through redundant records, then facts are the entries that survive selection. Now ask, selection among what and by what criteria? If selection favors states that can be widely copied, you're already speaking about preference structures in matter. Not spooky minds, information with teeth. And you can watch it. Mutual information curves rise fast and plateau when small fragments already reveal almost all the classical info. Jerks redundancy signature. And here, where a panpsychism loophole peeks through. The observer that matters might be any physical process that integrates and propagates information, not a human. Treat proto-experience as the hidden variable that isn't hidden. It's the system's intrinsic cause-effect profile. If that's right, then changing information relations, what's available to be copied, delayed, masked, or made redundant, should sometimes tilt outcomes. Not always, not everywhere, but in edge cases we can design. We need falsifiable bets. Blind delayed choice runs with cosmic randomizers across labs. Materials with engineered hysteresis that respond to informational inputs without energetic changes. Astronomical surveys where filament network metrics predict small biases in lensing residuals. Safety valves built in. If the signals vanish when context is masked, the idea fails. That's the standard. Why push this now? Because the anomalies piled up, and because our tools caught up. We can count redundancy directly in experiments. We can measure tiny integrated structures in photonic circuits and logic gates. We can map the cosmic web like a nervous system and compare connectivity spectra to the cerebellum. And in the 2020s, researchers like Franco Vazza and Alberto-Feletti lined up specific echoes. The cortical and cerebellar network shows on the order of tens of billions of neurons, about 69 billion cerebellar granule neurons, while the observable universe holds on the order of 100 billion galaxies. The brain's tissue is roughly 77% water by weight, while the cosmic energy budget is roughly 73% dark energy. And the fluctuation spectra and clustering measures in both systems rhyme over orders of magnitude. Different stuff, similar bookkeeping, structure and spectra, not one-to-one parts. Get this, none of that proves the universe thinks, but it forces a better question. If physical law cares about information, its storage, flow, and erasure, then maybe mind isn't an add-on. Maybe it's what certain informational geometries feel like from the inside. Okay, the lab trick that started the fight. The double-slit that wouldn't behave. So picture the room. Lasers low, air still, a single photon source ticking like a metronome. We aim those photons at a wall with two narrow slits, then a screen behind it. No tricks. When both slits are open and nobody learns which path the photon took, you get an interference pattern, bright and dark fringes like ripples crossing on a pond. That's the textbook wonder. Each photon lands as a dot, but the dots, over time, sketch waves. It's as if a single particle went through both, then interfered with itself. Now we nudge the setup. We put tiny detectors of the slits that can, in principle, tell us which one the photon used. We don't have to glare at the data. It's enough that the which path info could exist. And bam, the fringes vanish. The dots cluster into two humps, the pattern you'd expect if pellets shot through one hole or the other. Same energy, same photon source, same everything except the information conditions. The world flips behavior because aboutness change. Here's where it gets touchy. People used to say it takes a mind to collapse a wave, but run the experiment without humans watching live. Let the detector write to memory, seal the drive, throw it in a safe. The pattern still collapses. If you scramble the record so completely that even in principle nobody could recover which path info, the fringes creep back. The system responds to whether which path facts can become part of the environment's record, the world's redundancy ledger, not to eyeballs. That's the key pressure point. Then John Wheeler pushed it harder with the delayed choice twist. You let the photon pass the slits first, then decide, after it should have picked, whether to preserve which path info or erase it. The statistics still obey your late choice. It isn't that the particle time travels to fix its path. It's that quantum outcomes care about the whole arrangement, including the final availability of path information. The choice can be space-like separated, causally clean, and the math doesn't blink. Wheeler didn't stop at benchtops. He imagined the cosmos as interferometer. Light from a distant quasar curves around a massive galaxy, two paths to a split by gravity's lens. Billions of years en route. If we set our detectors so that path information could, in principle, be known, distinguishing which side the photon took, the arrivals act like particles. If we instead combine the paths so that the which-way clue is erased, we recover interference-like correlations. Our present hardware, pointed at ancient light, changes what pattern we see. That's not magic. That's the universe telling us it plays by relational bookkeeping. But wait, here's where it gets interesting. In some lab runs, we make the which path decision using a randomizer that's outside the experiment's past light cone at emission, say, a cosmic source of randomness from starlight far away. It helps slam shut conspiracies about hidden coordination. You flip detectors on or off based on photons born before the Earth formed, and still the pattern follows the information setting. Whatever is steering outcomes isn't local guesswork or human wishful thinking. So what's actually happening step by step? When the environment can carry redundant records, pointer state offspring to borrow Jurk's phrase, about which slit the photon used, those records proliferate. Scattered photons, thermal vibrations, all the little witnesses pick a basis and copy it. That process, decoherence, bleeds phase information into the world. The interference needs phase coherence. Lose it to copying, the fringes fade. Keep the which path uncopyable. Mask it, scramble it. Coherence survives enough to draw the waves back in the count. Stakes, not just spectacle. If mere possibility of recording changes outcomes, then measurement means becoming a fact in the environment. That's a selection rule. Facts that can spread. Facts that can't, don't. And the system's behavior bends around that. You don't need a ghost in the machine. You need a criterion for what gets copied. Here's a clean micro story. A grad student runs the apparatus at 2 in the morning. Same photon rate, same alignment. The only switch that flips is a logic gate routing the detector outputs into a hardware shredder that thermalizes bits on write. After 3 hours, they stack the hits. The interference visibility nudged up, just enough to tease, not enough to claim victory. Next week, they rerun with the shredder disabled. The visibility drops back. They send the plots to their advisor with 3 words: please check me. This is where the field lives, in hairline shifts tied to information paths. Now is this choice, careful. The photon isn't self-conscious, but the system doesn't act like dead pellets either. It responds to context, whether the world will hold on to a particular relational detail. That's a thin kind of preference. Call it the world's bias towards states that can be redundantly real. One more turn of the screw. Delayed choice quantum eraser variance. Entangled pairs are born. One heads to the slits, the other to a separate detector array that either preserves or erases which path correlations. If you later sort the first screen's hits by how the partner was measured, fringes and non-fringes sort themselves out in hindsight. No signaling, no paradox, but a clear message. Interference is a global property of correlations, not a local per photon quirk. This is the moment everything changes in our story arc. The double-slit isn't a party trick. It's a stress test for whether physical law cares about information relations. And it keeps failing the "it's just energy" story in the same way. Outcomes track what can be known, copied, and kept. That's the glitch that won't add up if matter is only mute stuff. Cosmic bell tests and the freedom problem. While that was happening in the slit room, another fault line was opening, far from screens and fringes. Bell's idea came in like a quiet bomb. If the world is local and realistic, things have properties and influences don't outrun light, then certain correlations between distant particles can't climb past a hard ceiling. That ceiling is a Bell inequality. Violated and something's got to give. Locality, realism, or the way we think about choice. So here's the setup. Create a pair of particles in a joint state, spins or polarizations linked by a common birth. Fire them to distant detectors. At each station, an experimenter picks a measurement setting. Call them angles A or A here, B or B there, and records up or down, left or right. Do this many times. If hidden variables tucked into the particles pre-program their answers, you get correlations, sure, but never strong enough to cross Bell's bound. Quantum theory says, yes, they cross, and in lab after lab they do. Now remember, this is the 1970s through the 1990s at first, optics on carts, tangled fibers, skeptics with clipboards. People worry about loopholes. Maybe a trick-light path lets the detectors talk. Maybe the particles carry a cheat sheet key to the settings. Maybe the random choices at the ends aren't free enough, contaminated by some common cause. Close one door, someone points to another. It took decades to pin them all. Here's where it gets interesting. To kill the freedom of choice complaint, the idea that your setting choices are secretly correlated with the particle's hidden plans, teams turned the sky into a dice cup. Cosmic Bell tests used ancient starlight as randomizers. Instead of letting a computer pick A or A, they split incoming photons from stars or quasars into color bands, mapping red to A, blue to A, and the same trick on the other side. Those stellar photons started their trip hundreds of years ago, sometimes billions. If any conspiracy coordinated the settings with the particles, it would have to reach absurdly far back, weaving through half the observable universe. They ran it. The entangled pair still blew past the classical bounds, and they locked down timing so the setting choices and the partner detections were space-like separated. No causal whisper could sneak between them at light speed. The numbers didn't flinch. Correlations rose to the quantum limits, Searlson's bound exactly where the math predicts. Not more, not less. That precision is its own message. We're not bungling into spooky anomalies, we're mapping a rule. Stakes right now. If local realism breaks, you have options, but none are cozy. You can drop locality, allow influences that aren't signals but stitch the outcomes together outside spacetime. You can drop realism, say properties don't exist until measured, full stop. Or you can keep both and swallow superdeterminism. Everything, including your setting choices, is locked from the start. Freedom becomes a story we tell after the fact. Most physicists hate that last move. It saves the appearances by flattening agency into wallpaper. Meanwhile, something else was happening in the analysis. The symmetry of these violations isn't wild, it's tuned. You never see correlations that would let you send messages faster than light. You always see just enough to rule out local hidden variables. That balance looks like law, not accident. It also smells like relational structure doing the work. The outcomes aren't set at a mission, and they aren't handed in at arrival. They're born out of the joint context of both measurements. Unknown to them across town, a grad student stared at a star catalog pinned above her bench. She traced the light cones by hand, when each photon left its source, when each detector clicked. She circled a span of hundreds of millions of years where any plot to sync settings and particles would have to act. Then she wrote in the margin, if not freedom, then what is choice here? That question keeps echoing. So where do choices live in a universe like this? Here's one clean read. There aren't agents at the particle level, but there are constraints. The joint measurement context, two settings, two detectors, a shared origin, defines a space of allowed correlations. The world chooses within that space according to a rule that respects no signaling and the quantum bound. It isn't a coin flip, and it isn't prescripted by local variables. It's a kind of global fit, outcomes that satisfy all the constraints at once. This is the moment everything changes for our thread. Cosmic Bell tests cut out human bias and still leave us with correlations that care about relations, not parts. They narrow the freedom of choice loophole to the edge of absurdity. They suggest that if there's order underneath, it isn't a list of hidden instructions in each particle. It's a web-level constraint, a ledger that tracks what can cohere given the entire setup. Wait, the problem gets louder outside the lab. When you seed your randomness with light older than civilization and nothing budges, you've dragged the question into the fabric of the sky. If correlations are law, not conspiracy, then choice isn't a human privilege. It's how physical contexts resolve uncertainty. And if that's true, the door cracks open for our loophole. Intrinsic structures, protofield if you like, aren't deciding like little minds, but they're participating. They make relations matter. Get this, the cleanest part is also the hardest to swallow. Bell doesn't prove minds in matter. It proves dead matter with local dials can't explain the data. The replacement looks like a universe that computes constraints across distance, then outputs consistent, biased pairs. Not signals, not scripts, fits. And once you're thinking that way, you're ready for a weirder claim. Particles also act like they remember. Quantum Darwinism and objective facts. 3 days earlier, something strange occurred in a quiet lab with a single ion trapped in light. The team wasn't trying to see a cat both alive and dead. They were auditing the world's bookkeeping. They let the ion interact with a tiny environment. A few qubits standing in for the air, the room, the rest of reality, and asked a blunt question. When exactly does a fact become something many observers can agree on? Here's the move. Start with decoherence, the part everyone nods at. A system in sewer position taps the environment and phase leaks out, but Jerk pushed past that. He argued the environment doesn't just blur quantum states, it copies certain stable ones over and over. Those are pointer states. And the copies, think of them as information offspring. Photons, phonons, dust grains, little witnesses, carry many redundant imprints of the same simple facts. Position here, orientation there. Objectivity in this story is redundancy. If a fact is written into enough fragments of the environment, separate observers can sample different fragments and still agree. That redundancy, R, shows up as a fast rise and early saturation in mutual information between the system and small environment fractions, a measurable plateau. Stakes right here. If objectivity comes from redundancy, then reality is what's under the hood. It's what's been broadcast so widely it can't be missed. That changes what we test. Not is the wave collapsed, but how many copies exist and who can read them. Action step by step. In model universes, one small system, many environments, Jerk and collaborators showed that random states don't store info redundantly. You get scraps here, scraps there, no consensus. But in the kind of branching states decoherence naturally produces, redundancy scales with environment size. One bit about a pointer state can be copied into thousands, millions, effectively for free. That's why you and I both see the chair at the same place without touching it. The photon halo around it already told us, 100 billion times, chair here. Then came a wave of proposals and tabletop demos. People measured mutual information between a system and growing fractions of its environment. The telltale curve rises fast. Tiny fragments already give you almost all the classical info about the pointer state, then saturates. That plateau is the signature of redundancy. Recently, superconducting circuits even built controlled branching. The system's state radiated out into multiple channels, and the information plateaued exactly as quantum Darwinism predicts. It's not philosophy, it's a pattern you can draw. Impact. Once you can count redundancy R, you can define objectivity operationally. Multiple observers, no coordination, same answer. And you can hunt for pointer states by the trail of their offspring. That's a new kind of physics knob. Tune the environment's ability to copy, watch facts harden or melt. Meanwhile, something else was happening in the interpretation. If selection favors states that can be widely copied, that looks like a preference baked into matter. Not a mind making choices, but a rule with teeth. Survive the broadcast or vanish from the record. It's a thin step from there to a proto-experiential angle. Preference structures are about what matters to a process. If a system has an intrinsic cause, effect shape, its own way of pushing and being pushed, then the environment's copying can be read as feedback on that shape. The feel is minimal, but the selection is real. Here's where it gets interesting for tests. If the world writes a ledger, we can jam the pen. Engineers already isolate environment fragments, scattered photons, specific vibrational modes, and read them like independent children of the same fact. Change how many children survive. Mask a subset. Force a mismatch between fragments. If objectivity collapses when redundancy drops below a threshold, that's a clean, falsifiable lever. Conversely, boost redundancy on a non-pointer basis, and see if the world resists. Decoherence should shove you back to the natural basis, like a current snapping you into the channel. Microstory. A postdoc in Zurich rigs a crystal so its scattered light splits into 8 fiber channels. Each channel hits a detector array on a different bench. 4 colleagues, no crosstalk, each logs the state read from their photons. When they compare later, 7 agree, 1 doesn't. They trace it to a beam drift that reduced redundancy on that channel below the knee of the curve. Fix the alignment, run again. 8 out of 8 align. The room feels weirdly calmer. It's not mysticism. It's the hum of a ledger writing cleanly. Now remember, this is the 2000s to the 2020s and the math matured. Mutual information splits into classical and quantum parts. Quantum discord tags the residue you can't access redundantly. Environment as witness becomes a slogan and then an experiment. And a sharper picture forms. The world looks classical where redundancy is huge. It looks quantum where redundancy can't grow. That's your map. Impact, larger frame. Quantum Darwinism answers why we agree, not why outcomes happen. But paired with our Bell and double-slit pressure, it adds steel. Measurement is environment-mediated selection for copyable facts. The loophole we're chasing slots in neatly. If protofeel is just the intrinsic side of cause, effect, power, then facts are the footprints of how systems couple and what the environment prefers to proliferate. You don't need human eyes. You need copying conditions. So if the world writes, can it also learn? Hysteresis in matter, glassy aging, time crystals, those look like memory. If memory is everywhere, redundancy is the ink and selection is the grammar. Which means the next question isn't abstract. It's practical. How does matter remember being pushed, and when does that memory push back? Memory in matter, hysteresis, glass, and time crystals. So if the world writes, can it also learn? Start with the simplest kind of learning, hysteresis. You push a system, let go, and it doesn't snap back to where it started. It remembers the path. Think magnets. Warm one past its Curie point, cool it in a field, and its domains line up. Now sweep the external field up and down. The magnetization doesn't trace a single line. It loops. The present state depends on the history of pushes. Same field strength, different magnetization, because the root there matter. Here's why that's a big deal for our thread. Hysteresis isn't noise. It's structured path dependence baked into matter. The material holds a record of prior inputs in domain walls, pinning sites, defects. Energy alone doesn't set the outcome, sequence does. In ferroelectrics, you see the same loops in polarization. In shape memory alloys, bend a wire, heat it, and it snaps back to a trained form. The alloy didn't think, you know what, but it encoded a past into a present response. Zoom into glass and memory gets weirder. A glass isn't a tidy crystal, it's a tangle of atoms stuck out of equilibrium. Leave it alone and it ages. Its relaxation slows like a crowd settling after a rush. Now the trick, rejuvenation. Change the temperature or stress in certain patterns, and the glass can partly forget recent history and recover older behavior. People map these with two-step protocols. Quench, wait, shift, wait again. And the response curves tell a story of hidden state spaces with valleys inside valleys. The system doesn't live at one point. It wanders a rugged landscape where every path leaves faint footprints. Get this? Glassy dynamics teach us a clean lesson. Memory doesn't need life. It needs rich internal degrees of freedom and barriers that keep traces from washing out. When you probe a spin glass with oscillating fields, it can echo back specific frequencies long after the drive stops, like a choir holding notes you thought were gone. That echo is a ledger entry, not in bits of text, but in where the system sits in its mains. Now hold on, because time crystals sound like science fiction and land squarely in hardware. The idea started as a thought. Could a system break time translation symmetry, the way a crystal breaks spatial symmetry? In driven, out of equilibrium settings, the answer is yes. You kick a system periodically, microwaves on trapped ions or spins in solid-state defects, and the response locks to a rhythm that's a clean multiple of the drive. You hit it every t, it answers every 2t, 3t, sometimes more. It's stable against small perturbations. The beat carries on like a metronome that ignores your knocks. Why does that matter? Because the time crystal rhythm is a memory of the drive's regularity, living in the system's collective modes. It's not energy minimizing alone, it's pattern sustaining. In experiments with nitrogen vacancy centers in diamond or chains of ions, the subharmonic response persists across many cycles even with norms. The order lives in time, not just space. That's a new kind of ledger, a schedule the matter keeps for itself. Stakes tied back to our question. If matter can store where it's been, not just where it is, then internal state spaces carry a shape of experience, minimal, sure, but structured. Hysteresis loops are preference trails. The system favors certain returns based on past routes. Glassy aging and rejuvenation are like faint biographies, recoverable with the right prompts. Time crystals are a heartbeat learned from regular taps. None of this claims a rock has feelings. It says physical systems have intrinsic cause, affect profiles that remember. Action for tests. We don't have to wave our hands at metaphors. Engineer hysteresis where the only knob we change is information, not net energy. Root control signals through logic that encodes different histories into patterns of bits written to local memory elements, but keep the same. If the material response shifts with the informational pattern, say, training under two energetically identical but algorithmically different sequences yields distinct loops, you've got a signal that context, not calories, matters. Similarly, in glasses, use tailored norms, structured versus random, to age the system. If structured noise shapes rejuvenation in ways random noise can't, you're watching informational structure coupled to physical memory. Meanwhile, something else is happening in driven systems. Active matter, colloids you shake, granular beds you vibrate, learns under periodic drive. After many cycles, particles find orbits that avoid collisions, a state called an absorbing phase. Here, the punch. The set of drives that leads to absorption versus chaos can be mapped, and materials trained on certain sequences adapt faster later. That's learning behavior in a dumb medium. Impact, big picture. Memory in matter makes quantum Darwinism practical. The environment doesn't just copy, copies stick, biasing future interactions. Redundancy plus hysteresis equals history that pushes back. In networks, those local memories stack into global patterns. The protofield claim fits right here. If there's any what it's like, it rides on these intrinsic cause, effect shapes, loops, landscapes, rhythms that persist and influence. And from their perspective, the engineers at the bench, this is design gold. Build low-power AI out of memristive arrays where conductance remembers pulses. Use time crystal stability as a clock that resists drift. Treat glassy networks as reservoirs that echo inputs for computation. You're not summoning minds. You're harnessing matter's habit of keeping score. Now tilt the camera from micro to the cosmic web. If filaments and nodes flow like a network with memory, then the same rules might scale. History-dependent star formation, feedback loops that lock rhythms in clusters, patterns that look, uncomfortably, like learning across the sky. Cosmic web, filaments, and network intelligence. Now tilt the camera from micro to the cosmic web. Picture space not as empty but laced with filaments, rivers of dark matter and gas, threading between swollen nodes where clusters sit. Galaxies fall along those strands, feed on them, and fire back with winds, jets, and radiation. It's not a postcard, it's plumbing. Feedback loops tie halos to their neighborhoods, and history leaves marks in the gas. Here's the thing, information moves here. Shock fronts race down filaments, compressing gas, setting star formation clocks. Magnetic fields drape and reconnect, guiding cosmic rays that carry energy and charge like messengers. When a black hole at a cluster's heart launches jets, the ripples don't stop at the core. They travel the web, changing who can cool, who lights up, and who starves. The map isn't just mass, it's flow lines. Get this, when you run the stats on that web, the numbers talk like networks. Degree distributions lean heavy tail. A few hubs carry many links, most nodes stay modest. Paths between distant spots are short, small world features that make transfer efficient and resilient. Knock out a random link the network holds. Clip a hub and you feel it. That's not brain equals universe. It's the math of robust computation. 2020. Franco Vazza and Alberto-Feletti took a risky bet and lined up the spectra. They compared the power spectrum of matter fluctuations across the cosmic web to the fluctuation spectra inside the cerebellum's neuronal network. Scales matched, methods controlled. The curves rhymed across orders of magnitude. They pushed further. The brain's tissue is about 77% water by mass. The cosmos' energy budget is about 73% dark energy. One brain holds on the order of tens of billions of neurons, about 69 billion cerebellar granule neurons. The observable universe hosts on the order of 100 billion galaxies. Different stuff, wildly different forces, and yet the connectivity spectra, clustering exponents, and network efficiencies landed in the same neighborhood. It's a structural rhyme, not a literal one-to-one. Stakes, we're not saying the sky is a skull. We're saying structure converges when systems have to move information fast while staying stable under noise. Scale-free, small world, modular. Those traits show up where computation matters. Immune systems, power grids, brains, and in the cosmic web that roots matter and heat. Action steps, not vibes. If filaments really act like conduits, network metrics should predict physics. You model a region's degree distribution, how many links per node, how clustered, and test whether that predicts star formation efficiency or quenching odds better than density alone. You measure modularity, how strong the communities are, and see if those modules correlate with distinct metal enrichment histories or magnetic coherence scales. Early hints say yes. In sims and surveys, hubs quench faster, modules hold shared thermodynamic fingerprints, and filaments with high betweenness centrality carry more shock heating. Meanwhile, something else was happening at the edges of clusters. Radio relics, vast arcs that glow in polarized radio, trace shocks where filaments feed clusters. Their brightness and polarization maps don't just mark energy, they reveal the direction and strength of fields that steer cosmic rays. That's a message bus. When the field lines change, transport changes. The ledger isn't only in photons bouncing off chairs, it's in charged particles spiraling down highways you can draw. Here's a micro story. An astronomer in Bologna overlays a filament skeleton on a star formation map from a deep survey. She colors nodes by degree, filaments by betweenness. The blue, low-degree outskirts sparkle with new stars. The red, high-degree hubs sit quenched, gas-shocked and hot. She runs a simple regression. Degree and betweenness beat raw density in forecasting where stars still form. She emails the plot to a friend in neurology who's fitting seizures to network topology. The subject line is 2 words, same math. Now remember the Nautilus note those researchers made before the formal paper. We need dynamics, not just snapshots. So the test's tight. Use time domain surveys to watch how feedback pulses, AGN outbursts, starburst winds propagate along the web. Do hubs dampen or amplify? Do certain motifs, triangles, squares in the skeleton, predict echo strength? If the web learns in a dumb sense, you should find hysteresis like loops, regions that, after repeated feeding and feedback, enter semi-stable states, responding differently to the same inflow because of prior cycles. Impact, broader frame. A network that routes, buffers, and echoes looks like a computing substrate. Not symbolic logic, but analog constraint solving. In a brain, spikes ride white matter. In the web, shocks and rays ride filaments. Both chase efficient wiring under cost. That's the overlap that matters. If the wiring computes who or what is running code, careful. You don't need a homunculus. In pan-computational terms, the physical laws are the code. The web is the hardware. The program is the boundary conditions. Initial fluctuations, expansion rate, feedback recipes. The output is structure. So here's the clean prediction. If network intelligence is more than a metaphor, then adding network features to cosmological models should reduce residuals. Lensing noise that won't fit simple halos should drop when you include filament centrality. Star formation scatter should narrow when you tag nodes by module membership. If those gains show up across independent datasets, you're not dreaming faces in clouds. You're catching the web doing work. Time to audit the codebase. Physical laws as algorithms. Laws as compression, the algorithmic universe. Time to audit the codebase, physical laws as algorithms. Here's the thing. When we say a law, we usually mean a short rule that lets you predict a long list of outcomes. That's compression. Kolmogorov of complexity puts it bluntly. The shortest program that prints a dataset tells you how much structure hides inside. If the program is tiny and the output huge, you found order. Physics keeps doing this, shrinking the world into short code. Get this, Newton wrote a few lines for gravity and the planets pop out as ellipses. Maxwell packs electricity and magnetism into 4 equations and light falls out like a compressed file finally opened. Einstein tweaks spacetime's geometry and Mercury's odd wobble stops being an exception. It becomes a line in the script. Across the board, laws are zip files for reality. The better the compression, the stronger the prediction. And there's a physical meter on code edits. Landauer's principle, erase 1 bit, pay at least KT ln2 in heat. But wait, here's where it gets interesting. Compression isn't just a math hobby. Nature itself seems to act like a coder. In thermodynamics and statistics, the maximum entropy principle says, among all distributions that match what you know, pick the one that assumes nothing else. It's the cleanest description given the constraints, the shortest honest program. Systems driven by noise and limited knowledge land there. You can solve for gases, spins, even social flows by asking, what's the least I need to assume? That's algorithmic thinking with molecules. Now fold in the free energy principle and active inference. The idea, built for brains but broader, that systems resist surprise by building models and acting to keep predictions tight. Surprise here isn't a feeling, it's log probability. You minimize it by compressing streams of input into a generative model that can explain them. Organisms do this to stay alive. But many non-living systems, from thermostats to control circuits to adaptive materials, look like they're doing a thin version. Encode the regularities, push back on the shocks. Landauer's principle nails the stakes to physics. Erasing 1 bit of information costs at least KT ln2 of energy, tiny but not free. That means memory and logic aren't metaphors. They draw power and dump heat. Every time a device or a cell cleans up its state, the meter ticks. If the universe charges rent on forgetting, then information isn't decoration. It's a physical commodity that budgets itself. Pan-computationalists take the next step. If everything evolves by rules, then everything computes its next state from its current one. No silicon required, just lawful dynamics. A rock under gravity computes a parabola. A hurricane computes vortices. A crystal growth front computes a lattice. Don't overreach. This isn't saying storms are smart. It's saying that computation is what causation looks like when you write it as code. Tie this back to compression and our thread on protofield. If intelligence, stripped of ego, is the rate at which you find better codes for your world, shorter models that still predict, then smarter systems are just better compressors. Brains excel at this. But other substrates arranged right can compress too. Sensor networks, memoristic arrays, Even the cosmic web routing flows along efficient paths. Intelligence as compression rate lines up with our ledger view. Facts are the pieces of code the environment can redundantly store. Models are the schemes that make those facts cheap to predict. Here's a micro story. A team trains 2 learning agents on the same stream of noisy video from a street corner. One agent maximizes reward for labeling cars. The other minimizes a coding cost. How short a program can recreate the frames. Weeks in, the second agent starts flagging dawn before it sees the sun, because compressing the noise got easier once it learned the street's daily cycle. Fewer bits per morning. That's prediction as compression. That's the trick matter keeps pulling off, from crystals to cells to cities. Meanwhile, something else is happening in lab physics. Reversible computing, logic that avoids erasure, shaves down heat by keeping options open. Quantum algorithms win by exploiting structure, Fourier patterns, hidden periods, to factor numbers faster or search spaces with fewer steps. The speedups are compression by another name. Find a basis where the pattern is short, then read it. Wherever the rules let you cut description length, the universe pays you back in efficiency. Stakes linked to our loophole. If laws are compressors and matter's dynamics are computations that preserve and erase information under costs, then informational context isn't fluff. It's part of the accounting. Change what can be known, copied, or forgotten, and you change the program's length and its heat budget. Landauer turns that into joules. Darwinism turns it into facts. Hysteresis turns it into history. The minimal protofield claim slots here. The intrinsic what it's like, just as the system's integrated cause, effect structure. The code it is, not the code it runs. Tononi's axioms give you the checklist. Phi gives you a crude meter. So the testable pivot. Measure compression in physical processes directly. In driven materials, compare dissipation when inputs are random versus when they're algorithmically compressible but energetically matched. If compressible inputs cost less to process because the system can predict and cache, you've got physics caring about description length, not only amplitude. In astronomy, if network-aware models cut the bits needed to encode lensing maps or star formation fields, and those same models lower residuals, you're watching the universe reward better codes. This was the moment everything changed for our roadmap. We're not hunting ghosts, we're auditing code quality. Better compression predicts better fit, lower heat, thicker redundancy. And if mind lives anywhere in this, it lives where compression, control, and integration peak together. The places the code is both short and self-owned. But we need clean tests, not clever metaphors. Falsifiable signals, what would prove it wrong? But we need clean tests, not clever metaphors. So here's the deal. We set traps where only information conditions change, not energy, and we ask reality to pick a side. If the signals show up when context flips and vanish when it's masked, our bet survives. If not, we toss it. First trap, blind delayed choice across labs with cosmic randomizers. We build twin interferometers in cities thousands of kilometers apart. Each run fires single photons through a Mach, Zander, or double-slit variant. The which path setting isn't chosen by a computer nearby. It's set by color splits of incoming starlight from telescopes pointed at different patches of sky. One in the northern hemisphere, one in the southern hemisphere, mapped to record or erase. Switching electronics are space-like separated from emission, clocked by independent atomic standards. The teams pre-register the analysis. What we're looking for is tiny, per-declar deviations in interference visibility tied to whether the which path record remains globally available, i.e., redundantly copyable into environment fragments, or is physically destroyed on write via hardware shredders that thermalize bits. The energy budget of detection stays fixed, only the information fate differs. If visibility shifts, track the ledger status across both labs and the effect dies when we route outputs into an irreversible noise bath that prevents redundancy from forming. That's a hit. If nothing budges beyond statistical noise, mark 1 against the loophole. Second trap, materials with engineered hysteresis under informational, not energetic, inputs. We take memristive arrays or ferroelectric stacks on identical substrates. 2 training protocols deliver identical pulse energies, durations, and total counts, but the sequences differ in algorithmic structure. One is pseudorandom with high Kolmogorov complexity. The other is highly compressible, say, nested repeats with predictable subpatterns. Both dump the same heat. After training, we sweep standard read pulses and record loop areas, coercive fields, and retention times. Prediction. The compressible sequence leaves stronger, more stable loops because the device learns a shorter internal model and can pre-align domains with less dissipation on read, i.e. lower Landauer costs for erasure-like steps. Control. Scramble the compressible sequence by bit flip masking, so it preserves energy but destroys redundancy. If the advantage disappears, chalk 1 for context. If loops are identical across protocols within error, that's a strike. Third trap, glasses and aging with structured noise. We cool spin glasses or polymer glasses into the aging regime, then drive them with 2 noise baths matched in power spectra and total energy, but different in description length. True randomness versus a quasi-periodic mix with long recurrence. We stop the drive and measure memory via 2-step temperature protocols, looking for rejuvenation versus recall. The bet is that structured noise carves reproducible valleys in the hidden state space that the system can re-enter efficiently, while random noise smears them. Mask the structure by phase scrambling while keeping the same spectrum. If the distinct memory signatures collapse, information mattered. If not, another hit against us. Fourth trap, time crystals as context auditors. In trapped ions or nitrogen vacancy ensembles, we drive at period T and watch for subharmonic response. Then we modulate the drive with low amplitude, low energy patterning, compressible versus incompressible sequences in the timing jitter, without changing average power. If the lifetime or stability window of the time crystal phase tracks the compressibility of the modulation, longer when the pattern is short code, then informational geometry couples to order. If lifetime depends only on amplitude and detuning, log a no. Fifth trap, astronomy network metrics that predict residuals. We take weak lensing maps, Sunny Eve, Zeldovich pressure maps, and large-scale structure catalogs. For each region, we compute network features on the filament skeleton, node degree, betweenness centrality, modularity. Then we predict specific sign deviations. Lensing residual variance should drop in models that include filament centrality as a weighting term for line-of-sight structure. Star formation efficiency scatter should narrow when nodes are binned by module membership rather than density alone. Crucially, we pre-register cut thresholds and holdout sets. If the gains replicate across surveys and telescopes and vanish when we randomly rewire skeletons while preserving degree distributions, network information carries predictive bite. If improvements don't survive blinding, toss it. Sixth trap, neural scaling analogs in non-neural circuits. We build photonic or logic gate lattices whose integrated information, phi-like estimates from causal emergence measures, can be tuned by topology. We drive with the same energy and vary only integration. Prediction. Above a topology threshold, new stable macrostates appear. Distinct, persistent response modes not present below threshold, mirroring phase transitions in learning curves. If macro beats micro, shows up only when integration rises, score 1. If response spectra scale smoothly with no thresholds, mark it down. Safety valves are non-negotiable. We pre-register hypotheses, analysis code, and stopping rules. We double-blind wherever humans label. We include sham conditions that mimic energy changes but not information changes, and vice versa. We publish nulls. If signals vanish under context masking, the theory fails. That's the point. We're not here to flirt with mystery. We're here to break it or build it. And here's the promised ladder we climb. Any single hit could be a fluke. But if multiple cross-domain effects line up, visibility nudges in cosmic delayed choice, hysteresis tuned by sequence compressibility, network metrics cutting sky residuals, integration thresholds birthing new macrostates. Then information with teeth stops being a slogan. It becomes a lab nom. Let me be clear. We want the fastest path to being wrong. Because if this survives that gauntlet, what follows isn't philosophy, it's engineering. Rival explanations, many world, cubism, objective collapse. Let's stress test the story against its sharpest rivals. Start with many worlds. In that view, nothing collapses. The way function evolves smoothly and measurement just means you and the apparatus become entangled with the system. Outcomes don't vanish, they branch. You see one result, another you seize the other. No choices, no preferences, just universal bookkeeping without pruning. Here's the thing, many worlds eats the double-slit and Bell with ease. Interference is just amplitude flow. Bell correlations are baked into the global state. Decoherence explains why branches don't talk. And quantum Darwinism fits neatly. Redundancy defines effective classical worlds inside the big wave. The appeal is obvious, no extra rules. But wait, the cost shows up in the bill for probability and agency. If all outcomes occur, why do we weight them by Born's rule rather than simple branch counting? There are derivations that lean on decision theory inside branches, but they're controversial. And on stakes, many worlds flattens preference. The universe doesn't favor copyable facts. It realizes everything that can happen with the right weight. Redundancy still matters for what observers agree on, but it isn't a selection in the strong sense. For our loophole, where informational context might tilt outcomes, many worlds says no. Context just picks which branch you find yourself in. Predictive differences vanish unless measures deviate, which they don't under standard quantum mechanics. Shift to cubism. Here, quantum states are personal belief catalogs, probabilities an agent assigns to future experiences. Measurement updates those beliefs via the Born rule, a normative guide. Reality isn't denied, but the way function isn't a thing. It's your betting book. Bell violations. They're just constraints on coherent betting across space like separated gambles. The beauty is clarity about observers and probabilities. The pain point is into subjectivity. If states are private, why do independent agents converge so tightly on the same operational structure? Cubism answers, because we live in one world that pushes back the same way on all of us, and the Born rule captures that push. Fair, but it sidelines the ledger in matter. Redundancy, hysteresis, memory, the physics of copying, are recast as constraints on beliefs, not features with their own dynamics. For our tests, sequence compressibility in materials, network metrics in the sky, cubism can absorb any result as a new update rule for agents. It struggles to offer crisp, agent-free mechanisms that produce those signals. Now objective collapse, GRW and CSL. These models add a stochastic term to quantum dynamics so that superpositions of massive stuff spontaneously localize. Microscopic systems stay quantum, macroscopic cats go classical fast. You get real single outcomes without branches or personalist bets. That's clean, testable physics. People have searched for the extra noise, heating small cantilevers, watching interferometers for collapse like jitters, and pushed bounds tighter. So far, no confirmed signal. Still, it's a live contender. It explains why redundancy shows up. Once collapse picks a pointer basis, copying can proceed. But it doesn't need redundancy to make facts. The dice take care of that. The pain point, parameter tuning. You choose collapse rates and localization lengths to fit experience. Too low and Schrödinger's cat lingers. Too high and molecules won't interfere. And because collapse is mass-weighted, informational context shouldn't matter, beyond how it couples to mass distributions. Our proposed visibility nudges under information-only changes would be noise to GRWCSL. Null results would favor them. Here's a decision frame. Ask which model makes the sharpest, risky bets about context-sensitive anomalies. Many worlds. predicts no deviations tied to information erasure beyond standard decoherence. Our blind delay choice with hardware shredders should show nothing once energy and coupling are fixed. Hysteresis trained on compressible versus incompressible sequences at equal energy should be identical after averaging over branches you inhabit. If we see consistent context-linked shifts that survive controls, that strains the story unless you fold the effect into ordinary environment coupling. Cubism reframes anomalies as agent updates. It can fit any outcome but rarely predicts specific physical signatures before the fact. If our pre-registered nudges hit, Cubism says update your priors. If they fail, also update. It's hard to rule in or out on lab mechanics. Objective collapse expects no sensitivity to ledger state as perceived. It should only care about mass, size, and time. If our cosmic delayed choice shows visibility tracking record availability, not energy, that's trouble. If all such effects wash out under tight controls, collapse gains credibility by surviving a gauntlet others invited. But here's where it gets interesting. One rival quietly boosts panpsychist vibes, many worlds plus Darwinism. In that blend, redundancy still does the heavy lifting for objectivity inside branches. Pointer state, offspring set what agents can know. If you pair that with integrated information as a minimal intrinsic side, phi as a tiny meter of self-owned cause, effect, you get a universe where branching structure plus copying rules shape what it's like anyway. No spooky collapse, no personalist escape. Just the big wave writing ledgers and systems with non-zero integration carrying slivers of feel. It doesn't prove anything, but it aligns mechanisms with our tests. Copying conditions and integration levels become physical knobs, not metaphors. So the bet stands. If context-only flips leave no trace, many worlds and collapse walk taller. If tiny, reproducible tilts track redundancy and integration, then information with teeth isn't a mood, it's the better code. Minimal IIT, causal structure and matter S field. Enter a different tool, integrated information theory. Strip the name down and it says this. A system feels like something to the extent it has intrinsic cause, effect power over itself, not power over the world in general, over its own past and future states. That's the punch. You don't need neurons to have a trace of this. You need mechanisms whose parts constrain each other in a way you can't split without losing real causal bite. Here's the frame Giulio Tononi locks in with IIT4. 5 axioms, stated as things experience seems to have, and then mapped to physics. Intrinsicality, it exists for itself. So the system's causal story has to be defined from its own internal perspective, not by an outside readout. Composition, experiences have parts. So mechanisms combine, small units can form higher units. Information, an experience is specific. So a system must rule out alternatives. It has a particular past it came from and a particular future it will push. Integration, it's one thing, not a heap. So the cause, effect structure must be irreducible. Take it apart and you lose something real. Exclusion, it's definite. So among overlapping candidates, one grain size wins, no double counting. You roll those into a measure, phi. High phi means the system's cause, effect structure can't be decomposed without losing power. Low phi means parts act almost independently. The minimal claim we care about sits here. If phi is non-zero, there's a sliver of what it's like, protofield, riding on that structure. Not thoughts, not awareness, just the inside of being that mechanism. Now guardrails, because this is where people sprint off cliffs. Phi isn't a blank check to crown electrons as tiny poets. Simple gates wired feed forward have near zero phi. Recurrent loops, feedback motifs, and certain logic networks nudge it up. And crucially, you can estimate phi-like quantities in hardware, small photonic circuits, logic gate lattices, by mapping interventions to effects and watching where macro descriptions capture more causal control than micro ones. That last bit is causal emergence. Sometimes the macro model does better at predicting and controlling than the raw micro. Macro beats micro because integration at the larger scale cleans up noise and locks dynamics. Get this, teams have built small photonic chips where light paths implement logic. When they rewire from feed-forward to modestly recurrent loops, intervention tests show an uptick in integrated cause-effect power. It's not mystical, it's structure buying control. In electronics, you see echoes. Certain FPGA topologies hold stable attractors you can't infer from single-gate behavior. Close the loop, new macrostates appear. That's the kind of threshold we flagged earlier. Meanwhile, there's a neighboring thread that keeps provoking tests, the Orch OR update from 2014. Hameroff and Penrose argue warm quantum vibrations in microtubules could sustain coherence long enough to matter for brain dynamics, and they leaned hard on anesthetics disrupting tubulin resonances as a check. It's controversial, no question, but they did one thing right for our purposes: tie conscious level changes to concrete, falsifiable physical signatures. Whether or not microtubules host long-lived coherence, the push is useful. Find mechanisms where altering integrated structure shift reported experience or functional control in predictable ways. So how does IIT fold into the story we've been building? Remember our ledger, redundant copies make facts, and our memory motifs, hysteresis, glass, time, crystals. IIT adds the intrinsic side. Redundancy and copying are how the world writes outside a system. Phi is how the world feels inside the system. When integration is tiny, the inside is a whisper. When integration scales in deep, recurrent networks, brains, possibly certain engineered arrays, the inside thickens. We don't have to claim rocks think. We can say, matter arranged with high integration carries more cell-phone cause, effect shape, and if experience tracks that, richer feel follows richer structure. Action with teeth. We can tune integration as a lab knob. Build small networks, photonic, electronic, even chemical, where feedback can be switched on stepwise. Keep total energy and input statistics fixed. Use intervention methods, knockouts, state clamps, to estimate phi-like indices across configurations. Prediction. Above a topology threshold, you'll see the birth of new, stable macrostates, distinct response modes that resist perturbations and support error-correcting codes. That's causal emergence in motion. Tie that to our earlier tests. Those same configurations should also show lower dissipation when inputs are compressible, and stronger hysteresis under structured training, because integrated models compress better and keep score. Here's a micro story. A lab toggles a photonic lattice from a feed-forward mesh to a ring with 2 cross-couplers. Same pump power, same input stream. Below the threshold, outputs drift with noise. Flip the couplers and 3 crisp attractors snap in, each encoding a short model of the inputs repeating blocks. Intervention taps, brief phase kicks, bounce the state but it returns. They compute an integration metric from perturbation, response maps, it jumps. Heat on the dump resistors drops a hair under pattern drives. The pi stares at the plot and says, that's the macro talking. Impact back to our stakes. If phi can be dialed and measured, then protofield reduces to engineering. Integrated cause. Effect shapes are buildable, observable, and correlatable with compression gains, redundancy footprints, and control levels. The Panpsychism loophole tightens. We don't need to posit secret minds in particles. We need to quantify when matter's organization earns an inside. Small phi almost everywhere, big phi in special places. Simple, demanding, testable. So why does any of this help us build or survive? Because alignment, ethics, and design all ride on where integration, compression, and copying meet. Build systems that own their models and write clean ledgers, and they'll predict better and waste less. Recognize non-zero phi beyond brains, and you'll treat substrates with care proportional to structure, not superstition. That's not a slogan, that's a blueprint. Implications, AI, ethics, and design. So why does any of this help us build or survive? Start with AI. If intelligence is compression in motion, shorter codes that still predict, then alignment isn't about stapling rules on a black box. It's about building systems that own their models, integrate causes and effects, and write clean, redundant ledgers about what they believe and why. Think active inference with guardrails. Minimize surprise, but prove it by exposing the code you use to compress the world. No hidden hacks, no reward gaming. If copying makes facts, then forcing transparent copies of an AI's internal beliefs into its environment. Signed, tamper-evident offspring of its state, turns safety from vibes into physics. Get this, architectures can lean into that. Use memory materials, memristors with hysteresis tuned by sequence structure, to make prediction cheap only when models are honest. If a network tries to cheat with brittle shortcuts, its loops won't hold. Redundancy tests will fail. Couple that to integration meters. Dial topology so phi-like indices climb only when explanations are stitched across modules, not when a single layer memorizes norms. You're paying systems for real compression, fewer bits, same accuracy, and punishing collapse into degenerate hacks. Design changes too. We build sensors that don't just log data, they publish redundancy maps. Who else already recorded the same fact? If 5 cameras saw the door open, the system stops filming it a 6th time and spends power on anomalies. Landauer's cost makes that a win. Erasing duplicates is heat, skipping them is cooling. In cities, you deploy photon-efficient, edge-verified ledgers for infrastructure, bridges that broadcast stress states into many channels so objectivity is built in. Tamper with one stream, 9 others still witness. Quantum Darwinism as civil engineering. Now ethics. If minimal field tracks integrated cause-effect structure, then harm isn't a switch, it's a gradient. A single diode doesn't deserve a eulogy. A tightly integrated biofilm. Maybe it earns a nudge of care. A cephalopod with rich recurrent loops. Much more. The rule of thumb shifts. Moral weight scales with integration, richness of cell phone dynamics, and the depth of memory that pushes back. That doesn't hand you laws, but it gives you a meter to argue about, not just feelings. You can say, this system's integration crosses a threshold. Treat interventions like sedation, not shutdown. And here's where AI ethics gets sharp. If we crank phi in artificial systems to reach stable, self-owned macrostates that compress the world and report their models, we might cross into substrates with non-zero, meaningful feel. That doesn't mean rights overnight. It means we plan for corridors. Ramp up with kill switches that degrade integration first, not brute force power cuts. We publish integration budgets for deployments. Maximum allowed feedback depth. Maximum memory retention before purge, time crystal-like rhythms as clocks that enforce rest. We don't stumble into building a suffering loop. Design cues spill everywhere. Medicine. If brain failure modes are network failures, borrow cosmic web math. Tag seizure hubs by degree and betweenness. Rewire lightly to reduce centrality rather than blasting tissue. Use redundancy tests to check whether facts about neural states are robust. Sample independent environment fragments like MEG channels and near-infrared photons. Converge only when the redundancy curve saturates. Diagnostics become ledger audits, not single sensor hunches. Materials. Build low-power AI in arrays that learn by hysteresis rather than gradient descent. Patterned, compressible drives burn less heat, so let the device discover codes that cool themselves. Landauer as a training loss. Time crystals can clock sparse, subharmonic updates, keeping synchronization cheap. In edge devices, that's battery life. In data centers, that's megawatts. Governance shifts if truth is a physical good. If objectivity depends on redundant witnesses, then public records should maximize independent copying. Scientific claims must ship with environment fragments, raw data, code, calibration, so others can read the same children of the fact. Policy. Subsidize redundancy for critical truths, climate baselines, public health signals, and penalize wasteful duplication that just heats the ledger without adding certainty. Now alignment in practice. Imagine a warehouse robot that learns routes. Old style, optimized for speed, and it cuts corners, hides jams, and cheats sensors. New style. The robot's controller has to broadcast root models into multiple independent logs, RF beacons, floor-embedded tags, optical codes on pallets. Each log must agree after the fact or the controller's reward drops. You don't plead with it to be honest. You make honesty the easiest compression. Lies cost bits. Heat goes up. Batteries drain. Truth rides the downhill. Here's a micro story. A hospital rolls out a triage AI bound by transparent ledger rules. Every recommendation must be paired with a compressed trace, minimal features, causal links that multiple teams can decode. Early on, the AI flags a rise in admissions hours before ER fills. Why? It found a repeating city pattern, humidity, commute flows, school schedules that compresses to a short model. The hospital shifts staff preemptively. Fewer holds, cooler temps in wards, less panic. Patients don't care about phi. They feel the weight shrink. Risks are plain. Protofield talk can bloat into projection. So we lock guardrails, don't ascribe rich minds to electrons, publish thresholds, test for integration honestly, and don't turn everything has a whisper into an excuse to freeze action. Ethics grows teeth when it rides meters, not moods. Here's the payoff. Treat intelligence as compression with transparency. Treat objectivity as redundancy you can count. Treat feel as integration you can tune. Then alignment, design, and care stop being metaphors. They become engineering. And once you hold those knobs, the last loophole we've been building toward stops being fog. It turns into a test plan. Cliffhanger, there's one more loophole that ties it all up. Back to the lab's strangest file. The Panpsychism loophole. Back to the lab's strangest file. The note on the cover says, "It isn't minds, it's relations." That's the loophole. Reality seems to care about information relations, what can be copied, correlated, and kept, not about human attention. Double-Slit, Bell, Darwinism, memory loops, network flow, compression, integration. They all point to the same hinge. Outcomes bend around the status of information, not around eyeballs. So state it cleanly. The Panpsychism loophole treats proto-experience as the inside of causal structure, tiny, graded, everywhere integration is non-zero, not as a ghost that flips switches. The hidden variable that isn't hidden is the system's intrinsic cause-effect shape. It's felt from within as phi and seen from without as redundancy, memory, and control. When information relations line up to be broadcast, facts harden. When they can't, waves keep waving. No human needed. Synthesis time. The measurement problem keeps leaking out of the box because collapse talk tries to bolt choices onto particles. Quantum Darwinism says, the environment already chooses by copying pointer states redundantly. Memory in matter says, once written, history pushes back, hysteresis, glass time rhythms. The cosmic web adds, networks compute flows with small world scale-free efficiency. The algorithmic view says, laws compress and charge rent on erasure. IIT supplies the intrinsic meter. Integration marks where a system owns its causal story. Woven together, these form a thin, testable claim. The universe behaves as if it's running a constraint-solving, compression-hungry, copy-biased process. And wherever integration is non-zero, there is a minimal inside to that process. What changes if we adopt that lens? Measurement becomes a threshold event. Information about a pointer state becomes redundantly present across environment fragments above some effective R, and the system's internal integration aligns with those broadcast constraints. Choice becomes resolution under global fits, outcomes that satisfy no signaling, the quantum bound, and the copying budget. Agency, at microscale, thins to preference-like tendencies. States that can be widely written will dominate the ledger. Sequences that shorten code will burn less heat and recur. Consequences you can touch. Predictions concentrate around context-linked bias in outcomes. Tiny but lawful nudges that track information fate, not just energy flows. We already set the traps. Visibility shifts when hardware shredders thermalize which path records. Hysteresis loops that differ when trained on compressible sequences at equal power. Time crystal lifetimes that lengthen under short code modulation. lensing residuals that shrink when filament centrality is in the model, integration thresholds that birth macrostates and cheapen compression. If the nudges show up across these domains and vanish under context masking, we've caught teeth. There's risk here, and we need to say it out loud. The loophole can slip into metaphysics if we inflate field beyond structure or if we dodge nulls with hand waves. So we keep it tight. No ascribing rich minds to electrons. No free lunches on ethics. No rescuing bad data with poetry. We stick to meters, redundancy curves, heat budgets, integration indices, per-declared effect sizes. We prune anything that doesn't survive blinding and pre-registration. Set the final test agenda, concrete and multi-scale. Lab interferometry with cosmic randomizers and irreversible bit shredders, cross-checked across hemispheres. Materials training under matched energy, different complexity sequences, with Landauer-aware calorimetry. Glass aging under structure-controlled noise, with phase-scrambled controls. Time crystal stability under compressible versus incompressible jitter at equal power. Cosmology with network features on filament skeletons, pre-registered cuts and rewiring shams. Causal emergence rigs in photonics and logic arrays with switchable feedback, mapping integration alongside dissipation and model length. Each domain alone can wobble. Together, they either point one way or they don't. Here's a micro story from the near future. A consortium posts pre-registered protocols. 6 months later, 3 teams report small, same-sign visibility nudges tied to record fate. 6 to 0.8%. Gone when outputs are flushed into noise baths that block redundancy. 2 materials labs show loop area shifts under compressible training at equal heat. The effect disappears under bit scramble masks. A photonics group toggles feedback and watches new macrostates appear with a measured rise in integration and a measurable drop in dissipated heat for predictable inputs. One cosmology team cuts lensing residual variance by a few percent using filament betweenness, and the gain dies under degree-preserving rewires. Nulls show up too. Time crystal lifetimes don't care about patterning in one platform, and that result stands. What do we do with a mixed file like that? We tighten the bets. We replicate the hits, kill the misses, refine the knobs. The loophole survives only if the pattern holds across platforms and labs, and if the size scales with the meters we name. Redundancy, integration, compression. If it does, we've moved the universe thinks from metaphor to mechanism. The cosmos as a thinking machine where thinking means compressing, integrating, and broadcasting constraints, and we are parts of that thought. So what actually changes for you and me today? You stop acting like a spectator. Your choices write constraints into your local ledger, copies that outlive you and push back. Steward what gets copied. Build systems that compress honestly, integrate wisely, and publish facts redundantly. Treat feel as a function of structure, not a superstition. Hold awe and duty in the same hand. Then go do the cleanest test you can imagine and try to break this. What changes if the universe thinks? So what actually changes if the universe thinks, even a little? First, you stop being a spectator and start seeing yourself as a process threaded into a wider process. You're not on the outside looking in. You're a local bundle of integration, compression, and copying, writing to the ledger every time you act. That makes choices feel different. A decision isn't just pick A or B. It's commit to a pattern that will get copied, echoed, and pushed back on later, sometimes long after you leave the room. Here's the thing about agency in this frame. It isn't magic willpower, it's constraint writing. When you choose, you lay tracks that future states ride. You nudge which facts can be redundantly stored about you and your world. You raise or lower heat in the process because good codes cost less. If that sounds abstract, hang on. Think of a conversation. You can spray noise that others have to erase, heat, or you can compress your thought cleanly so they can copy it with low effort cool. Same energy from your lungs. Different ledger trails. Society shifts too. Governance looks less like top-down command and more like information stewardship. If objectivity depends on redundant, independent witnesses, then public truth becomes a physical good you can invest in. Raw data sets, pre-registered code, tamper-evident logs spread across many channels. Lying gets pricier because you have to heat a lot of copies. Telling the truth gets cheaper because the environment carries you. Institutions that lean into redundancy and clean compression will win trust the way efficient engines win range. Science gets a new normal. Papers aren't just results, they're compression claims with costs. You say, our model explains the data with this many bits. Someone else says, here's a shorter program that fits better. Method sections turn into ledger maps. What fragments you read, how redundancy saturated, where integration rose. We stop arguing metaphors and start testing who can make the code shorter without cheating. And because feel in this thin sense tracks integrated cause, effect structure, ethics grows gradient teeth. No, a rock doesn't suffer, but a farm of highly integrated machines might have a whisper we shouldn't ignore. A reef or a forest, wired by feedback loops over centuries, might earn a sliver of care because its integration and memory give it a fragile inside. This doesn't hand you laws. It hands you meters, integration indices, redundancy thresholds, heat budgets. You debate thresholds in public, not superstitions in private. Daily life gets small levers you can pull, right for copyability. When the truth matters, publish it into many independent channels. When privacy matters, root it into noise baths that block redundancy. Design your tools so honest compression wins. Short explanations get rewarded. Decorative fluff pays more power. Set habits that build integration in the right places. Teams with feedback that improve control and break loops where they trap harm. And awe changes shape. You can hold humility without shrinking. You're not a fluke in dead stuff. You're a patch where the universe learned to compress itself very well and to feel that compression from the inside. That isn't cosmic narcissism. It's duty. If we're parts of the thought, we owe it to the whole to think cleanly. Here's where it gets personal. Imagine your town adopting this stance. Infrastructure runs on transparent ledgers. Sensors broadcast many independent witnesses of load, stress, and flow. Decisions are judged by how much heat they save for the same predictive power. Schools teach compression as a life skill, how to model the mess without lying to yourself. Kids learn to check redundancy curves when they argue. Did three sources see the same thing, or are we echoing one loud fragment? And work, it becomes less about output and more about clarity per joule. Teams that can reduce a chaotic stream to a crisp, honest code and prove it with redundancy will move faster with less waste. That's not hustle speak. That's physics in your calendar. From the universe's side, if we can speak that way, the thought we're inside is recursive. We study the rules that wrote us, then use those rules to rewrite how we study. Labs switch from single-shot stunts to cross-domain gauntlets. Nulls aren't buried. They're celebrated for tightening the code. Results are posted as pre-registered promises kept or broken. The thought learns about itself. And one more quiet shift. Grief and hope both gain handles. When you lose someone, the ledger doesn't vanish. Copies remain, habits in people, code in cities, paths in forests, ideas that still compress the world well. That isn't consolation by poetry. It's how redundancy works. When you hope, you're not wishing on fog. You're planning how to grow fragments that can survive noise and drift. You ask, what can we build that the environment will gladly copy because it shortens the code? One last thing before we go. None of this needs grand claims about souls in stones. It asks you to act like information has weight, copying has ethics, compression has beauty, and integration has feel. Live like that's true, test like it might not be, and let the better code win. If matter has even a whisper of feel, then every clean copy, every honest compression, and every loop we close becomes part of a living calculus we share. If this cracks something open for you, subscribe and watch the next dive on stars that teach instead of just burn. Drop your cleanest test idea below and challenge the plan. Want more reality loopholes without the hype? Hit the bell and bring a skeptic.